Hello and welcome to E2E Classes, your gateway to empowered learning. Today, we are going to embark on a fascinating journey into the world of physics, focusing on a very intriguing concept known as length contraction. For those who might be hearing about this for the first time, don't worry. We'll be breaking it down in simple terms, making it very easy for everyone to understand. This concept is a fundamental part of the theory of relativity, introduced by the famous scientist Albert Einstein. It tells us how objects appear shorter in the direction they are moving, but only if they are traveling at speeds close to the speed of light. Imagine driving a car at an incredibly fast speed, so fast that you're nearing the speed of light. According to length contraction, your car would appear shorter to someone watching from the roadside. Sounds interesting? Let's dive deeper into this concept, understand why it happens, and explore some interesting examples to make it crystal clear. So, grab your notebook, keep your mind open, and let's get started on this exciting journey through one of the most fascinating aspects of physics. Let us consider two reference frames, S and S prime, such that S prime frame is moving with constant velocity v with respect to S frame along the common x or x prime direction. Let us consider a bar AB lying in the S prime frame. The bar is at rest with respect to the observer in the S prime frame, so this observer would measure its proper length L0. Whereas, the bar is moving with respect to the observer in the S frame, so the observer of this frame would measure a shorter length L. This phenomenon is known as length contraction. Further, we are going to provide a proper definition of length contraction and going to derive its formula to help you write quality answers in university examinations, if required. Thereafter, we will solve some numerical problems based on it for your competitive examination preparations. Here is the definition of length contraction. Length contraction is a relativistic phenomenon, according to which length of an object, as measured by an observer in motion relative to the object, is shorter than its proper length. The proper length is the length of the object measured in the rest frame of the object, that is from the frame in which the object is at rest. This effect is only apparent when the object is moving at speeds approaching the speed of light, and it occurs solely in the direction of motion. Mathematically, length contraction is described by the formula L is equal to L0 times square root of 1 minus v square over c square. Where L0 is the proper length of the object, L is the contracted length, v is the relative velocity of the object with respect to the observer, and c is the speed of light in vacuum. As the quantity square root of 1 minus v square over c square is always less than 1, so L is always less than L0, that is, the length appears to be contracted. The concept highlights the relativity of spatial measurements and underscores the interdependence of space and time. Now, let's derive the length contraction formula, a concept you may need to understand and apply in your university examinations. Imagine two reference frames, S and S prime, where S prime frame is moving at a constant velocity, v, relative to S, along the common x or x prime direction. It's crucial to note that it is the relative velocity between the two frames that matters, not how this velocity is achieved. Therefore, any scenario where the S prime frame moves with velocity v relative to the S frame demonstrates the same effect. Consider a bar A, B lying in the S prime frame along the x prime axis, which is aligned with the direction of relative motion. The spatial coordinates of the endpoints of the bar, as measured from the two frames, are summarized in the table below. The endpoints A and B of the bar, as measured from the S prime frame, are at positions x1' and x2', respectively. From the S frame, these endpoints are measured at positions x1 and x2, respectively. Therefore, the length of the bar as measured from the S' frame is x2' minus x1', which represents its proper length, denoted as L0. This is because the bar is at rest relative to the observer in the S' frame. Conversely, the length of the bar as measured by an observer in the S frame, to which the bar is moving, would be L equals x2 minus x1. So we have L0 equals x2' minus x1' and L equals x2 minus x1. Now we will apply Lorentz transformation. We recommend you to also watch video lectures of E2E classes on Lorentz transformation. According to the Lorentz transformation formula, x prime equals the fraction of x minus vt over the square root of 1 minus v squared over c squared. Using equation 3 in equation 1, we get L0 equals the fraction of x2 minus vt over the square root of 1 minus v squared over c squared, minus the fraction of x1 minus vt over the square root of 1 minus v squared over c squared, equals the fraction of x2 minus x1 over the square root of 1 minus v squared over c squared. Using equation 2 in equation 4, we get L0 equals L over the square root of 1 minus v squared over c squared. Therefore, we get the length contraction formula as L equals L0 times the square root of 1 minus v squared over c squared. Now, let's explore a fascinating concept known as length contraction through an engaging illustration. Imagine a disk moving at a speed close to the speed of light. According to the phenomenon of length contraction, the diameter of the disk along its direction of motion experiences the greatest amount of contraction. Conversely, the diagonal perpendicular to the motion remains unchanged. Meanwhile, every other diagonal contracts to varying degrees, falling between these two extremes. Let's say the original diameter of the disk is 6 centimeters. When it moves at a speed of 0.3 times the speed of light, its diameter along the direction of motion contracts to approximately 5.724 centimeters. As the velocity increases, this diameter becomes progressively shorter. At a speed of 0.95 times the speed of light, the diameter along the direction of motion shrinks to 1.87 centimeters, which is just 31% of its original size. Intriguingly, the diameter perpendicular to the motion remains unaffected. We hope you found this lecture both enlightening and engaging. We are excited to delve deeper into the topic of length contraction in our next session, where we'll tackle some intriguing problems to further our understanding. Please, if you haven't already, consider subscribing to the E2E Classes channel and liking our videos. Your support helps us bring more content like this to you. Thank you for watching and stay curious.